So in section 5.7, we finally addressed the complex zeros of real polynomials. So this chart that you see on the board is not actually on the handout itself, but just to give you a little bit of background. The handout starts off with asking the question, let's consider the following list of numbers. So the list of numbers is -1, 0, the square root of 2, 3/2, 5, and then 3i. And it wants to know which of the following numbers in that list are complex numbers. So what I'm going to do is I'm going to take those numbers and I'm going to put them into what we call a Venn diagram of the number system. So our real number system and our complex number system is made up of the following components. So you have the natural numbers. Those are the numbers that you would count by. So 1, 2, 3, 4, 5. So the 5 is going to get put into there. The whole numbers adds in the 0. So a whole numbers is the set of natural numbers plus 0. When we add in the negatives, like -1, we have the set of integers. The rational numbers add in the terminating and repeating decimals and fractions. So that would be the 3/2. The irrational numbers involve our radicals. Those are non-terminating, non-repeating decimals. Pi is also an irrational number. And when you add those all together, you get the set of real numbers. Now, sitting over here is the set of imaginary numbers. So 3i would be an imaginary number. When we combine them all together, we get the set of complex numbers. This is actually a trick question. All of these are already complex numbers. So we've been dealing with complex numbers the entire course. We just haven't officially stated them as complex numbers. So we're now going to go find all the zeros. So the whole point of section 5.7 is we're going to add in the imaginary zeros and have all of the zeros. And we're going to call them complex zeros because the number system we're dealing with. So a complex polynomial, a bunch of definitions and theorems to start off again. It's a polynomial where the coefficients are complex numbers and the variable x represents a complex number. So these are those complex zeros we're going to be finding. The fundamental theorem simply tells us that every complex polynomial function has at least one complex zero. That's as long as it's a degree n or greater. So we're now going to go find those complex zeros. There's another theorem on the box. It says that every complex polynomial function of degree n greater than or equal 1 can be factored into n linear factors. They might be repeated factors. That multiplicity that we saw clear back in section 5.1, we'll see that again here too. So we can simply take those complex polynomials and factor them into linear factors, which we'll be doing today. That means that every complex polynomial function has exactly n complex zeros, some which may repeat. One of the things we have to lay the groundwork for is the fact that when we have these imaginary solutions, that they occur in what we call conjugate pairs. So to lay that groundwork, let's consider the polynomial function f of x is equal to x squared plus 9. So in previous sections, we would just call this a polynomial function. In this section, we're going to call it a complex polynomial function. And again, it simply means the number system that we're dealing with in terms of an answer. So what are its zeros? Well, if I asked you to solve this equation, you would take x squared plus 9, you'd set it equal to 0. X squared is equal to a -9. You'd square root both sides and get x is equal to plus or minus 3i. So the complex zeros of this polynomial function are positive 3i and a negative 3i. Notice they occur as a conjugate pair. So whenever I have a positive I term, I will also have a negative I term. They all come from quadratics, which is why you get that plus or minus like that. So the conjugate pairs theorem simply says if we have a polynomial whose coefficients are real numbers, notice the real numbers on the coefficient here. If one of the zeros is a plus bi, then a minus bi must also be a 0. They will occur in conjugate pairs for us. Okay, that's all the heavy theory. There's actually a lot of theory involved in all those little theorems, but we're just going to start applying them and see where we go with that. So example 1 says information is given about a polynomial function whose coefficients are real. Let's find the remaining zeros. So for part A, it tells me, well, we have a degree 3, and some of the zeros are a 4 and then 3 plus 5. Well, we know by the fundamental theorem that every that the degree of the polynomial dictates how many answers we have. Well, it's a degree 3, so I need 3 answers, 3 solutions, 3 zeros. Well, I have 2 of them. Well, luckily the conjugate pair theorem tells us that if 3 plus I is a 0, then the remaining 0, the one they didn't give me, is its conjugate, which would be 3 minus I. And it's literally just that simple. That's all they want on that problem. Part B says, okay, what if we have a degree 4? And we know that the zeros are 2 minus I and also a negative I. Well, then the remaining zeros have to be the conjugate pairs to those guys. So the first one would be 2 plus I. That's the conjugate pair to 2 minus I. Again, you don't change the sign on the 2, only the sign on the I. And then the conjugate pair to negative I would be a positive I, and those are the remaining zeros. Now we can actually write a polynomial. So our next example is going to have us form the polynomial. So example 2 says, let's form a polynomial function with real coefficients having the given degree and zeros. So this time it is a degree 4. We have zeros that are 3 with a multiplicity of 2. And then they also tell me 4i. Well, so that means 3 appears twice. So that's 2 of my zeros. I have 4i, which is another one of my zeros. So they gave me 3 zeros, but I know I need 4 of them all together. So the one that is missing is the negative 4i. That's the conjugate pair to the positive 4i. Well, now they're actually asking me to write the polynomial. So we're going to take those zeros and we're going to put them in factors. So f of x for our polynomial function is equal to, we would have x minus 3, and we're going to put a square on that one because it says it's a multiplicity of 2. We're then going to take that 4i and write it as x minus 4i. And the negative 4i is going to come down as an x plus 4i. So again, each time I go to put a 0 back as a factor, I change its sign when I go to put it in. And the reason is they're saying if x is equal to 4i, it's a solution. Then when you bring that 4i back over to the x, you have x minus 4i, which is this factor. So that's why you switch that sign to put it back into its factor. It's linear factor. Okay, well, with the online homework, you can't leave it right here. It's going to want you to expand and multiply this all out. So what I'm going to do is do some grouping. I'm going to FOIL these 2 together first, and then I'm going to FOIL these 2 together. So when I take x minus 3 and multiply it by x minus 3, I'm going to get x squared minus 6x plus 9. When I multiply x minus 4i times x plus 4i, I'm going to get x squared minus, well, the positive 4i and the negative 4i in the middle are going to cancel. So I have 4i times 4i negative. It's going to give us negative 16i squared. But we know that I squared is equal to a negative 1. That comes from the fact that the square root of negative 1 is equal to I. If you square both sides of that, you'll get an I squared and a negative 1. So we're going to replace this I squared with a positive 6. Sorry, we're going to replace the I squared with a negative 1, which in turn makes this into a positive 16. So x squared minus 6x plus 9, x squared plus 16. And then all we need to do is multiply these 2 polynomials together. So these 2 factors together. Let's take the x squared and multiply it by each of these terms. That's going to give me an x to the 4th plus the 16x squared. Again, I took x squared and multiplied by the x squared and by the 16. Now I'll take the negative 6x and multiply it by both of those terms. So negative 6x times x is a negative 6x cubed. Negative 6x times 16 is 96x minus 96x. 9x, now we're multiplying 9 by both terms. So 9 times x squared and 9 times the 16 will give us a 9x squared, and 9 times 16 144. Now all we have to do is collect like terms. So we have x to the 4th. I'm going to put that negative 6x cubed next so that they're in descending order. That's our standard form, descending order. Minus 6x cubed, 16x squared, and the 9x squared is going to give us what, 25x squared. I have minus 96x plus, there it is. There is the 4th degree polynomial whose zeros are 3, that appears as a repeated root. So we repeated roots of a multiplicity of 2, then a positive 4i and a negative 4i. So we're doing kind of the opposite of what we did just the other day.